Welcome everyone to my talk about centralized service-oriented architectures in the automotive domain. My name is Darko Durisic. I come from Volvo Cars from Gothenburg, Sweden. And I will present you today some of the challenges that we in the automotive domain need to face in the future, and also how we plan to tackle those challenges, mostly by presenting you what changes we need in the system architecture. So my talk will be admittedly a bit more technical than the majority of talks today, but I hope you will still like it. So if we talk about the products that we are developing, well, of course, we develop cars, but it's not really the same as cars that we have been developing in the past 10 years, or especially 20, 30, 40 years ago. Today, we like to refer to our products as computers on wheels, because they really have a lot of software and hardware electronics in them, not just traditional mechanics present in many decades. So here, this data which I'm showing you, and numbers, they're already a couple of years old. So we have more than one gigabyte of onboard binary code, excluding the infotainment domain, the gadgets that you have in the car. Today, it's already a couple of gigabytes for sure. We have more than 150 electronic control units, basically computers executing certain software functions in the car. This is one of the things that we are actually trying to reduce in favor of having fewer computers, but more powerful computers, which you will see in a little while. We have more than 100 million lines of software code. And just to give you a comparison, so this is comparable to the biggest passenger aircraft today, Airbus A380. And definitely significantly bigger than, for example, all the rovers that we are having on Mars or fighter jets. So the question, of course, is what happens tomorrow? Will we have even more software tomorrow? And this is one of the things I will be talking about today. But let's take a look at the evolution of the electrical system in cars, basically since 100 years ago, because in 1927, at least for Volvo cars, it all started with this beautiful model here that you can see. And you can see that the electrical system is extremely simple, basically presenting the battery, powering up the headlights and taillights, and of course, the most important thing, the horn. And then if we talk about today's vehicles, Volvo cars like XC90 here in the top right corner, you can see that we have a completely different picture of the system, of the electrical system. Here you can see those 150 different computers responsible for executing very many different functions. So I think this sketchy phase summarizes very well where we are today and where we want to be tomorrow. Today we have a computer like cars, and there is no discussion about that. But tomorrow we actually want to go even one step further and have a car-like computer. We accept today and know already today that software is and will be our most important assets that we are working with. So we want our traditional car manufacturer companies to also become software companies. There are some studies showing that already today, more than 80% innovations in vehicles are related to software. And this comes both in terms of functionalities, but also non-functional properties. You can take just safety, for example. In the future, we are expected to save significantly more lives with active safety mechanisms that will actually even avoid collisions than we did with passive safety mechanisms like three-point seat belt, which, by the way, is also invented by Volvo cars, or airbags, and so on and so forth, which also saved significant amounts of lives in the past decades. So I will. What becomes important, I have another slide showing you these things, but what I want to say very clearly is that there will be new business models coming in the future, already today, especially having in mind the autonomy of vehicles that is expected in a short future. We also, because of that, need to think about the architecture of the system. We need to work more on, for example, decoupling hardware and software, because they have different development loops, and they actually can have different life cycles. And of course, we need to think about the process, how we work, and so on and so forth. So if we talk about what is expected from cars in the future, one of the biggest expectations, of course, is the autonomous vehicles. And we have them even today to a very large extent. We have very many vehicles that are able to handle traffic jams fully automatically. We have also some vehicles that are able to drive on certain highways fully automatically. But of course, in the future, we are expected to move even to the higher autonomy levels, where we will actually not even require from the drivers to pay attention to the road and look at the road, which of course opens up very many other possibilities that the driver and the other passengers can do during drive time. Then it's connectivity, one of the requirements basically for autonomous drive. We want all the information between our cars to be shared between them, but not just between Volvo cars, hopefully in the future between all different car brands as well, and not just between cars at all. Also, we want to have a smart road infrastructure. We want to exchange information with the mobile devices, and so on and so forth. It's also very related to this to these customer expectations as well, because customers today, they really expect the car basically to behave like their mobile phones. All the apps, everything that they have in their mobile phone, they also want to be able to use it in their cars and have a seamless integration between mobile phone and the car. Then we talk about electrification. We at Volvo Cars are convinced that this is the future in the automotive domain. You've probably heard also very tough requirements from different regions in the world about sustainability and zero emission in the US, Europe, Japan, and China. So this is something that is definitely coming really soon. I believe that we are, in some cases, about regulations, we talk about 2030, some maybe 2035. But we are not expecting in the midterm future and long-term future to be able to earn any money in developing internal combustion engines, both petrol and diesel. And then, of course, we need to handle new players in the market, new old players in the market. So by this, I mean, you see that Google, Apple, they're coming into automotive industry. NVIDIA. So some of the old players are now really into the automotive domain. But of course, we have newer ones. Even Uber is now not a new one after so many years, but we really need to see with which ones we from the traditional car manufacturers want to collaborate with, and which ones are actually competition to us. And then finally, we need agility. So we have a lot of technological challenges, but some of them are also about ways of working challenges. How do we achieve this? Well, I will be talking today about these three core ingredients: agile development, modularization of the product architecture, and centralization of the product architecture. So I'm not saying those three are the only things we need to focus, but they are definitely three of the most important, or at least very important ones to be considered. So when it comes to agile development, we at Volvo Cars are on the journey to change our traditional V model waterfall-based development towards agile since 2017. And that was basically based on these principles of having a backlog handling, because we know that we cannot do everything. So we need to know what is the most important thing to do and what gives us the biggest value. We also understand that everything comes from empowered teams. This is the biggest asset that we have within the company. And we want them to be empowered to be able to make decisions on the how, technical how, but also to be able to make decisions on the ways of working how that affects internally the team. We want continuous integration of both software and hardware. Of course, here we mean mostly software, but not just software. We also want to test new hardware. And we want to lift this up to the next stage and do the continuous deployment of at least our software functionalities directly over the air to the vehicles, to the customers, perhaps do some A/B testing and feedback the information directly into our development. And all this is based on the modular architecture, which is the core ingredient number 2 that I will be talking about. So here you can see our transformation. This is based on the Scaled Agile framework. I'm sure that many of you are familiar with Scaled Agile framework, so I will not spend much time here explaining, other than just saying that this is a possibility to scale team methods like Scrum or Kanban to the full organization. I will be focusing on the architectural part here. So we have architectural roles on all different levels of SAFe. We have system architects, which are basically working on a team of teams level. We have a solution architects working on the large solution level. We call this level product streams. For example, product streams in delivering hybrid propulsion or electric propulsion or infotainment. We have an enterprise architect, and one of the additions we did was this global architecture team, because we want, of course, to put responsibility as close as possible to the implementation into different product streams and agile release trains. but we also need a group of complete architects making sure that everything fits together and works well. And that's basically my role. I'm the product owner of the global architecture teams at Volvo Cars. So second thing, second core ingredient, here we talk about the modular product architecture. What we want here is we want to go away from working towards projects, for example, towards different cars. We don't want our development to go for a specific car. We want to develop products that will have their own life cycle, and then, of course, fit them into different projects, into different vehicles. It's not that easy, of course, it takes some work, but still, it's very important that we decouple this product development from the project development. And how do we do that? Well, we do that by having a modularized architecture. We have different modules, both software modules, hardware electronic modules, but also hardware mechanic modules. And then, of course, in theory, we just need to compose everything and build a car like using different Lego bricks. In practice, of course, it's a little bit more difficult, but still, it's very important that every product, like infotainment system or, as I mentioned, electric propulsion, that they have their own development cycle, and that we just take the best and the latest and the greatest version of it when we want to build a new car. So these modules, they're owned by different agile release trains, and they belong to different product streams or solutions. It's very important, in order to be able to fit them into the system, they need to have a very clearly defined interfaces. And those interfaces are shown here. Basically, what we want here is we want a service-oriented paradigm in the definition of these interfaces. So we want to go away from a traditional periodic communication between different parts of the system. Every 5 milliseconds or 10 milliseconds. And we want to go into more service-oriented architectures, where we will, first of all, discover what services we have in the car at runtime, not at the build time or pre-build time. And then maybe even having multiple services providing the same information, like vehicle speed could be calculated based on the wheel turn or GPS. And then based on different quality of data, we have the ability at runtime to choose which service provider we would use. So it's very important to move into these service-oriented architectures. And of course, we don't want to have a periodic communication always dragging our bandwidth and everything else. We want to be able to subscribe to different changes in the modules and be notified by change in data. And finally, the third ingredient, the third core ingredient is to move away from today's domain-based architectures into more centralized architectures. You can see here in the left picture the domain-based architectures. And then, of course, we want to do it in different steps. These are two bigger steps, but our idea is actually to move away from revolutionizing our system architectures between every bigger car project, usually 4 to 5 years. Instead, we want to evolutionary develop architecture based on the same ground principles, but of course improve hardware and software. So you can see here an example of a domain architecture currently in Volvo's vehicles. So you have a domain master. These are all computers called ECUs, electronic control units. You have different domain masters, for example, for body or comfort domains, handling the doors, windows, seating, and so on. You also have an infotainment domain and its own domain master, and then they serve like some kind of a guarding number of smaller ECUs connected with the more traditional automotive electronic buses like CAN and Lean. And these bigger domain masters, they are usually connected with the high-speed network. In this particular case, it's FlexRay, but it could be Ethernet as well. And then what problems do we have here? Well, first of all, we build this based on the logical domains. Infotainment, body, comfort, as I mentioned, HMI, they are logical domains, which means that there's a lot of communication between different domain masters and different ECUs, because they are not built based on their location, but instead based on the functionality. And of course, this results in a lot of kilometers of cables in the cars. You can actually even see the form of a car by just looking at the cables running through the car. So how do we want to approach this problem? Well, we want to centralize our architecture. We want instead still to have certain ECUs in the so-called mechatronic rim. But these ECUs and software here should be extremely simple, just responsible for handling a specific device, hardware device like actuator or sensor, camera, sensor, or door, and so on. But what we really want is that all decisions, all vehicle-wide decisions, are done in this central computer, vehicle computation unit, which is a very powerful CPU with actually several CPUs and having different cores. And we also want to take responsibility for this software, to do it in-house, which is a big comparison to what have been traditionally done in the automotive domain, where, for example, in those domain architectures, you had each ECU being delivered and developed by different suppliers. And then, of course, we have those vehicle integration units, which are just used to actually connect the data from the mechatronic rim ECUs to the core computer. And you can see there is a reason why this is step one here, because we didn't manage to integrate everything in this core computer. We still have an infotainment system basically running outside, and we also have the autonomous drive system currently running outside of the core system. And of course, one of the benefits here, there are many benefits. We will significantly reduce also cable harnesses, because this is based on the geographical location. You don't have different VIUs based on different logical functionalities in the car. You actually connect ECUs to the VCU via VIUs that is the closest to this ECU in the mechatronic rim. So this will significantly reduce cable harnesses, but also reduce complexity, or at least make this complexity manageable from the system's point of view. And then, of course, we have other steps in the future that we are going to work with. This is just showing the next step. You can see at least that the VCU is the same. We can have different computers here. We can have multiple VCUs. But at least in the first step, we're thinking about integrating the AD, autonomous drive system into it, maybe even the infotainment later on. And what we also want to do is we want to make those VIUs here a bit smarter, because they're here used basically just to gateway the information from the mechatronic rim to the core computer. But what we want them is to be a little bit smarter and have some software functionality, so that we can perhaps directly connect sensors or actuators to zone controllers. And also they will be able to have a power supply, to give power supply to all the ECUs behind the zone controllers, and serve some kind of a switch on and switch off in the system. Okay, this is my last slide. I hope I'm running on time. So what I want you to take home from this is basically those three big things that are currently happening in the automotive domain. We can see that not just at Volvo cars, we see it in other companies. It's agile development, very important, because without agility, without flexibility, and this also involves, for example, contracts with certain suppliers that we will have developing usually mechatronic rim units and devices. It needs to be flexible, and we need to anticipate changes and be able to react to changes, not always think that we are starting a new project whenever a small or medium change occurs in the system. And then modularization. The key about in modularization is to go away from developing things for a specific project or a car, but instead have clear products in the system which have their own life cycle, and then that we can in theory just put together like Lego bricks when we want to build a new car. And finally, going away from a significant amount of low power processing CPUs in the car into centralized system, where we have a significantly fewer computers, but we have a more powerful core system that is able to handle the vehicle-wide functionalities.